All right, the next thing that we want to do is look at how to take the data from first order kinetics and turn them into linear graphs, because linear graphs are a lot more easy to work with, um, a lot easier to work with than are the exponential decays. So let's take a look at those. All right, so the graphs we looked at before, right? We looked at kinetic data. If we had the concentration of A as a function of time, it had kind of a curved shape to it. But curved graphs are a little bit difficult to work with because, one example, if we've got a point here and a point here, and we know that we have an exponential decay, it's not really clear whether the line is something like that or whether it's something like that. Um, and also, if we know this point really well, and we know this point really well, or trying to estimate the value of some point in the middle, it's a lot more difficult when you've got a curved graph when we're trying to estimate a point um, around here or around here, right? If you compare that to a graph, gosh, yellow is really the only thing that shows up very well here. So I'm going to stick with yellow. Now, if you've got a linear graph like this, right, and you know that your data comes through here, if you've got any kind of a point in the middle here and you want to extrapolate, it's really easy to see exactly where that intermediate value is going to be. It's a lot easier to do that with a linear graph than it is with a curved graph. Right? But also, with this graph, we'll see that we can pull out some special values from that, which will be helpful. So let's look at how we can get a straight line graph out of the data that we had on our for the first order kinetics. You recall before we had a data table with time and concentration, and we plot concentration as a function of time, and we get that kind of curved exponential graph. All right. So what we want to do is find a way to graph this that looks a little bit nicer and is easier to work with. So to do that, we're going to do a linearization on this first order kinetic equation. The equation that we're working with is concentration of reactant at time t is equal to the initial concentration of that reactant times e to the minus kt. Okay. What we're going to do to this equation is we're going to take the natural log of both sides, and this gives us natural log of a at time t, which is equal to the natural log of, initially I'm going to write this out as the whole right hand side of the equation. A to the 0 times e to the minus kt. And so on the right hand side we've got log of a sub 0 e to the minus kt. And one of the things we saw when we were talking about logarithms is that the log of a product is the sum of the logs. So if we take the natural log of e sub 0 times e to the minus kt, that gives us the sum natural log of a0 plus natural log of e to the minus kt. Right. And so we'll keep this as it is, natural log of a0. And then this last part here, natural log of e to the minus kt, is just minus kt. And now with the right hand of the equation, I'm going to keep the left hand as it is over here. And on the right hand, I'm just going to take the two terms and just switch the order. So this is going to be minus kt plus natural log, the natural log of the initial concentration. So now, what's nice about this, if we take this final equation here, so far it doesn't look any better. We just made it messy with a whole bunch of logs and stuff. It looks more complicated, so it doesn't really look like an improvement. But if we make a graph, and we will put time on the x-axis just as we did before, and on the y-axis, instead of the concentration of the reactant, we're going to plot the natural log of the concentration of the reactant. Okay? So that means that this here, natural log of the concentration, is our y value, time is our x value. And if you look at the form of this equation, you'll see that this is in y equals mx plus b form, or what we call slope-intercept form. That means that when we plot the natural log of the concentration of the reactant on the y-axis and the time on the x-axis, we're going to get a straight line like that, and the slope here is negative k. Okay, and k, of course, is the rate constant. Rate constants are always positive, so the slope here is going to be negative. When you work through these, make sure you remember that slope is negative k. So the slope will be a negative number, but the k is positive. Okay? And if you take this line and extrapolate back here, this intercept, y-intercept, is the natural log of the initial concentration. Usually we don't need to calculate that because usually the initial concentration is given to you, but if you had a problem which you only had a couple of points in the middle of the reaction and you didn't know the initial concentration, you could use this straight line calculation to extrapolate back and figure out what that initial concentration was. All right? Okay, let's take a look at an example. All right, so here's the same data that we had in the previous video. So this is the data for that the formaldehyde reaction reacting with water to make methylene glycol. And if we want to plot this as a linear function, we just make a new column entry here, the natural log of this concentration. And for each one of these, we just use our calculator, natural log of 0.45. And since all these numbers are less than 1, which is typical, you can have concentrations that are greater than 1, but usually they're less than 1. And so with these numbers being less than 1, the natural log is going to be negative. And so for this first one, we get negative 0.0799. For the next one, 0.413, we get negative 0.885. Okay. And also, let me make the point here. When you take the log of a number, you lose the units. So all of these numbers here are unitless. Okay. All right. Calculate those if you want to fill out the rest of the table. I've got the numbers. I'm going to go ahead and jump ahead to the next slide where we've got the numbers. Okay, so let's see what we can do with this. Once you've calculated the log of all of those different concentrations, you can put them into a table. So you should have something that looks about like that. And then if we plot all of these, we get this nice linear graph, and we can connect all of our data points and see that we get a nice straight line. we said before. Slope is negative k, and the intercept is a natural log of the initial concentration. All right, let's use this graph to calculate the value of k. I'm going to make another copy of this graph a little bit bigger so that we can use it a little bit better. Let's take a look at that. Okay, so here's our graph, and here's our plot. Okay, and to calculate the value of k, we just need to calculate the slope. So I'm going to switch over to red. I'm going to just pick 2 points on this line to define our triangle, right? And it's often convenient to pick things where they cross grid lines. You don't have to do that, but it makes it a little bit easier to define these points. Okay. And remember that the slope is the change in the y-coordinate divided by the change in the x-coordinate. And this is our change in y, and this is our change in x. Okay, I'm going to go back to the yellow because it shows up a little bit better. All right, so our slope is going to be the second y value, right here, and that y value is -2 minus the first y value over here, which is, we'll just say -1.2. Okay. Over the second x value. And the x value here looks like it's about 700. And unlike the y-coordinate, the x-coordinate does have units, and those are seconds. Okay. And the first x-coordinate right here, that happened to fall. We're in that line, so that's 250. Okay. So our slope is going to be -2 minus 1.2. That's minus a minus, so we can make that a plus. This will be -0.8 over, what's that, 450 seconds? I believe it is. I'm going to double check just to make sure. All right, yep. Minus 450 seconds. And so when we calculate that, wonderful. Okay, we get -0.00178, and note the units for reciprocal seconds. Okay, so I'm going to clear this out a little bit, make some room. All right. So remember that the slope is -k, so -0.00178 reciprocal seconds equals -k, and therefore k equals 0.00178 reciprocal seconds. Okay. And that is essentially the same value that we had yesterday. This is the same data that we had in the previous video. All right, so we should get the same value. Our value is off a tiny bit here in that last decimal. The actual value is 1.72 times 10 to the minus third, and here we got 1.78 times 10 to the negative third. The reason we're off a little bit is because when we're using the graph, we have to pick a couple of points on there and estimate the values. And our estimation actually was pretty good, pretty darn good here. But we are off just a tiny bit. And that's fine. That's fine. I'll show you another way to do this that you can do without the graph. And let's take a look at that next. All right. The other thing that we can do, if we've got data, if all we have is a graph, like we had before, then what you need to do is just look at the graph, find a couple of points, and calculate the slope the way that we did before. But the slope is really just a ratio of the changes in the x-coordinate to the changes in the y-coordinate. So we can get the same thing from this raw data. And to do that, all we have to do is just pick any two data points for no particular reason. I'm going to pick this one here at 100 and this one here at 600. And I'll call this point number 1, and I'll call this point number 2. Okay. So we can also calculate the slope by looking at this. The natural difference in these natural logs is going to be our change in the y-coordinate, and the difference in times is our x-coordinate. So using this data from the table, just take the second value of y, which is negative 1.831, minus the first value of y, and divide by the second value of x, minus the first value of x, and that's going to give us, again, we've got minus and minus here, so we can make that plus. That gives us, in the numerator, we get negative 0.86, and again, those logs are unitless. And in the denominator, we get 500 seconds. And when we divide them, we get negative 1.72 times 10 to the minus 3 per second. Okay, and remember, the slope of the line is negative, so that's why we're getting a negative value here. But k is negative the slope, so you just change the sign, and this means that k is 1.72 times 10 to the third reciprocal seconds. Okay, lovely. Okay, and that's the same value we got yesterday, which is wonderful. And you probably know what I'm going to tell you about this table, right? Since k is a constant, and constants by definition are constant, that's why we call them that, right? You could get the same result by choosing any of these pairs. So you might next try this point and this point. Okay? Or you might try this point. 0 will work. You might try this point and this point. So while you've got this here, go ahead and choose, another data pair, maybe a couple of data pairs, and try doing this calculation again and see if each time you do it, see if you get the same value for k. Okay, you should, and also remember your units in the calculation. Okay. All right, here's a sample problem. This is for a different reaction. You see this time the time is in minutes, right? If the time is given to you in minutes, then you can just go ahead and use minutes. So just calculate it and use minutes as the units for your rate constant. You don't have to convert everything into seconds. Okay. So the question here is use the data provided to calculate the value of the rate constant. All right. Go ahead and pause and work through that. And I'll do the same thing here, and then we can compare our results. All right. When I did this, I chose the point at 10 minutes and the point at 30 minutes and calculated the slope as delta y over delta x. Delta y is the difference of these two values. Delta x is the difference in those two values. So that's what I have over here on the right. Delta y on the top, delta x on the bottom. That gave me negative 1.711 divided by 20 minutes. When I divided that through, I got negative 0.0856 in the numerator, or 0.0856 per minute. Okay? And the value on that slope was negative, but of course, like we said before, because k is negative the slope, and k is positive, so k is 0.0856 per minute. Okay. Now, like I said, as long as you've got units of reciprocal time, you don't have to convert everything into seconds. So there's our value for k. You probably chose different values, maybe by coincidence. You chose the same ones I did. But regardless of which ones you chose, you should have got something really close to that. It might, again, just because of rounding error, it might be off a little bit in that last digit, but it should be pretty darn close to that. If not, give it another shot, check your math again. Okay. All right. And let me say this too. You can have a problem like this for which the first part is calculating the rate constant using the log data, and that's what we've done here. You could have a follow-up question which might say something like calculate the concentration of the reactant at 15 minutes. Okay, so if you had that, very often these kinetics problems have multiple parts to them. Right. So if you wanted, if the second part said, what's the concentration of A at 15 minutes, right? Then you could just go back to the equation that we had yesterday. Okay, for that second part, right? Because we've got the initial concentration, that's right here, 0.22. We just calculated K using the log data, and so now you have everything you need to calculate concentration of A at 15 minutes. Okay. And if you go through that, if you want to, at 15 minutes, the concentration is 0.061 molar. Okay, you might take a minute, give that a shot, and see if you get the same result. All right. There's not really a lot here in this one. This is a short video. The important thing here is just that we were able to take this equation and convert it to an equivalent form And this does two things. One is it allows us to graph the concentration as a function of time in a way that gives us a straight line. Straight line is important for a couple things. One is straight line graphs are just easy to work with. The second thing is, and I don't think I mentioned this before, but I'll say it now. If you plot the natural log of the concentration as a function of time and you get a straight line, that's a really good way to prove that a reaction is first order. If you just look at concentration as a function of time and you get that curve, it's kind of hard to tell whether it is first order or second order. But if you plot natural log of the concentration as a function of time and you get a straight line, then that's considered proof that you get a first order reaction. Right? So this gives you a way to plot these in linear fashion to demonstrate that you've got a first order. And then once you've got that, you can calculate the K from that data either by calculating the slope of this line, delta y over delta x, and K is negative slope, or if you have the data in a table, just calculate the natural logs of the concentrations and pick two values on the table, calculate the difference in natural log and divide by the difference in time, and that will also give you K. Okay. All right, that's it for this one. We'll be back with one more video about first order reactions in a little bit.